ഓക്കെ സോ നമ്മള് ലാസ്റ്റ് നിർത്തിയെടുത്തുന്ന തന്നെ നമുക്ക് തുടങ്ങാം. ഇപ്പൊ ചില ക്വസ്റ്റ്യൻസ് കഴിഞ്ഞ പ്രാവശ്യം കൂടുതൽ ഡിസ്കസ് ചെയ്യണം എന്ന് പറഞ്ഞത് വേറെ MCQ രൂപത്തിൽ ഇപ്രാവശ്യം ഉൾപ്പെടുത്തിയിട്ടുണ്ട്. വിൽ നോട്ട് മിസ്. പിന്നെ കഴിഞ്ഞ ക്ലാസ്സിലും ലാസ്റ്റ് 2 ക്വസ്റ്റ്യൻസ് ഒരുപാട് പേർക്ക് ഇരിക്കാൻ സാധിച്ചിട്ടില്ല, സമയം എക്സീഡ് ചെയ്തതുകൊണ്ട്. അപ്പൊ അതും വേറെ ഫോമിൽ ആ സെയിം ക്വസ്റ്റ്യൻ വന്നിട്ടുണ്ട്. ഡിസ്കഷൻ വരുമ്പോൾ ഒന്നും അത് ക്ലിയർ ആവും. യു വോണ്ട് മിസ് ഈവൻ ഇഫ് യു മിസ് the last half an hour of the last class. Okay, so the easy question വെച്ച് തുടങ്ങാം. Not that easy, but a bit easy compared to the other questions. അപ്പോൾ നമ്മൾ ഈസി ക്വസ്റ്റ്യൻസിന്റെ ഒരു സെറ്റ് കഴിഞ്ഞ പ്രാവശ്യം ചെയ്തു. അപ്പോൾ ഇപ്രാവശ്യം നമ്മൾ ചെയ്യുന്നത് മീഡിയം ലെവൽ ക്വസ്റ്റ്യൻസും ഡിഫിക്കൽട്ട് ലെവൽ ക്വസ്റ്റ്യൻസും ആയിരിക്കും. സോ like in all the entrances നമുക്കൊരു 50% questions is like everyone can answer. ഒരു 30% will be a bit tough and 20% will be very difficult. അപ്പോൾ you have to take care not only about these 20% very difficult questions, but you should always take care not to miss the easy ones. Difficult കിട്ടി easy ones miss ചെയ്ത് പോയാലും it will be like very difficult for you to come up in the ranks, because 1 or 2 മാർക്കിന്റെ വ്യത്യാസത്തിലൊക്കെ ഒരുപാട് റാങ്കുകളിലായിരിക്കും ഡിഫറൻസ് വരുന്നത്. Okay, so this actually belongs to the a little bit difficult type, not very difficult. You can type in your answers as you did in the last session. Question is, I think the screen is totally visible, right? You can see the screen, right? There is no issue with my screen or voice, right? Okay, fine. So this is a question in a community of and like I said last time, every word in the question is very, very important. Even if a single word changes, the answer can change. And if you make a mistake and you reach an answer, that will be in your options 95% of the times. Okay. So when you see an answer in the option, you will straight away go for that. But you have to be very careful whether that word was this or that. So in a community of population 5,000, 40 people of 40 different households developed an infection with a new strain of influenza virus, having an incubation period of 7 to 10 days. Total number of people in these 40 households were 150. 10 days later, 90 new cases of the same diseases were reported from these households of the same disease. That is the same, they're telling us that it's the same infection itself. So we can take it totally. 25 more cases were reported from these households after a month. Total number of cases reported after 1 month from this community was 1024. So this is how a typical influenza spreads, because it's very fast. So they're asking us a secondary attack. Basically, it's simple, but if you look at the choices, you might get confused. If you know the idea, you can straight away go to the answer. Otherwise, you can think. Just give you a bit of time. Yeah, we are answering C, so we will see. I actually done a bit of writing for you, so that when I explain, you might not be able to keep up with me. So I have just written down some answers for you, some explanations for you. So we'll see one by one. So the question is about secondary attack, right? So secondary attack rate, I mean, I have written this because even if there are some audio issues from my side, the answer is very clear to you. Okay. So this is not my, this is my rough writing. I have not checked for the grammatical and the kind of say the beautification of sentences, and just for you to understand. Okay. The question is about secondary attack rate. Secondary attack rate is the number of at-risk individuals developing the disease within 1 incubation period from a primary case. So the first case that we identify is often we call it as index case. Okay, that is another MCQ. The first case we identify. So what is the name for the actual first case in the community? We might start with the index case, but later we might realize that somebody else was infected from whom the index case got infected later during the investigation. What do we call that case? Anyone? The actual first case in the community. If you've seen the movie Contagion, you will get the answer. Or okay, it's not the primary case. Primary case is the index case. That is the case with which we start our investigation. And the secondary cases are those cases who get infected from the primary case. The actual first case is referred to as case 0, from where it started. Case 0. So it's not a total epidemiological term. It's basically it's used in investigations to understand that index case is different from the initial case. Most of the times for surveillance mechanisms are really good. Index case will be same as the initial case. So it is said 40 people from 40 different households had this disease who would serve as the primary case for their families. I mean, at a time we diagnose this, we have 40 cases at hand. It's not just one case, it's of 40, we know there are 40 cases. So there are total 150 people in all these households together, of which 40 were already having the disease. That point you should not miss. So at-risk population here is 110. 40 are already infected. 110 people are about to get infected who are at risk. Nothing has been specified about the vaccination status of any of these 110 people. So we can assume that actually it's a new virus and it's a virgin population and all. Or otherwise they would have told us that 10 of them were vaccinated or 20 of them were vaccinated. In that case, we have to consider them as not at risk. So they will not form a part of the denominator. The number of new cases that developed within one incubation period is 90. So the secondary attack rate is given by 90 by 110 multiplied by 100% percentages. Once a disease has been induced in a population, the index case secondary attack rate gives an estimate of person-to-person transmission of the disease. This is another MCQ. Secondary attack rate gives an estimate of person-to-person transmission of the disease. A disease with a high secondary attack rate is potentially epidemic. If it is really high, it can even become a pandemic. So that is denoted, the how many cases are infected by one case is denoted by another thing called R0, which is your basic reproductive number. It's a bit advanced epidemiology, so I'm not going into that much. But you have to just realize that there is something called R0 or the basic reproductive number, which tells you whether a disease is going to stay stable in the population or it is going to become an epidemic or a pandemic and all. So if R0 is high, then if one person infects, say, 2 people, then it is going to become an epidemic. So if R0 is between 1 and 2, it has a potential to become the epidemic. If it is 1, it means one person infects one person, it will become endemic and stay stable in the country. For an epidemic to die down or a disease to vanish, the R0 has to be less than 1. Okay. So secondary attack rate is also used to study relatives of someone with a non-communicable disease to study the pattern of such diseases. Please mute, someone is speaking. And to get an idea about the genetic and environmental risk factors. So this was asked once as an MCQ about secondary attack rate. There was a choice which told us that it can also be used in non-communicable diseases. So we invariably write it as false because we learned the secondary attack rate is only for the communicable diseases. So it is also used in non-communicable diseases. So the wrong choice would have been something else in that. Okay. This is an easy one, right? Going to the next question. In a study, 1,000 smokers were followed up for development of emphysema and 200 cases were picked up. In the control group of 1,000 non-smokers, 20 people developed emphysema. Total population was 225,000 and the prevalence of smoking in the general population was of 40%. The researcher calculated all possible risk estimates, including odds ratio. How much would be the attributable risk? This is the question. Yes, you already know what this is. It's a simple question, but a bit twisted. That's all. You already known the basics of epidemiology and odds ratio, relative risk, everything, right? It's all basic, simple things that you learn. If you have any doubt, you can stop me and ask me, right? You can type in your doubts. So 1,000 smokers were followed up and 200 cases were picked up. Control 1,000 non-smokers, only 20 developed MS. They also given us additional information about total population of 2,25,000 and prevalence of smoking as of 40%. It is out of 100 people, 40 people smoke. Question is, how much would be the attributable risk? This can be done using just your thought process. You don't have to write and all. You have the clear idea. So these questions can be asked even if there is no space for your mathematical calculations. Yes, only Dhanasri has typed in the answer. Irene has also answered. So they're all going wrong. In a way, you will actually go wrong in your thought process. Okay, they are saying 40 and one person, two people are saying 90 also. Okay, so head up your mind, it's either 40 or 9. It's good. So we will see. Attributable risk is the risk that can be attributed to this exposure alone in producing the outcome. That means if we are measuring the outcome after an exposure, the outcome could be due to the exposure as well as due to some other reasons or some other exposures rather than our exposure. So in general population, even if there was no exposure, some people will have the disease or develop the disease. That is, smokers will develop lung cancer, but non-smokers will also have lung cancer to an extent. So that risk is called the background risk. Okay. So attributable risk is mathematically given by the difference of incidence among exposed and incidence among non-exposed. And this can be expressed as a percentage of the incidence among exposed. That is, among the incidence among exposed, what percentage is due to the exposure itself and not due to any other cause. So the incidence among non-exposed is the background risk, which is there even if our current exposure is totally avoided. So your incidence among exposed is 200 by 1,000 and incidence among non-exposed is 20 by 1,000. So typing error. So an incidence of 20 by 1,000 would still occur even if nobody smoked. That is the background risk. Okay. The attributable risk of smoking is 200 by 1,000 minus 20 by 1,000 is equal to 18 by 1,000. When this is expressed as a percentage of the incidence among exposed, there is actually 180. So some typing mistakes are here and there. So incidence among exposed, we get 890 by 1,000 by 20 by 1,000 into 1,000, which is equal to 9 by 100 or 90%. So typing error might actually confuse you, but you get the idea, right? 200 by 1,000 is the, I just did this in a very, say, bit of a hurry so that you can see what is there. So 200 by 1,000 is actually your incidence among exposed. Incidence among non-exposed is 20 by 1,000. So difference would be 180 by 1,000. Right. It will be 18 by 100. So now we have to see what percentage of that is 18 by 100 is how much of 20 by, so 18 by 1,000 actually is how much of 20 by 1,000, right? So we will get the answer as 9 by 10 actually. That is 9 out of 10 cases are due to smoking alone. So relative risk is calculated as the ratio of incidence among exposed to the incidence among non-exposed. In this case, it is 200 by 1,000 by 20 by 1,000. So it is how much is the incidence among exposed divided by how much is the incidence among non-exposed. Okay. And how much is that? We will always say relative risk in a numerical digit. So 200 by 20, that is 10. So if they ask you for the relative risk, it is 10. When 10 is the relative risk, and when you see that 10 times the cases are occurring higher, that means it would have occurred as, say, if 10 cases occur, this is the simplest way to imagine what is being said. If 10 cases are actually occurring in a community due to one exposure, if relative risk is 10, then the incidence among exposed is 10 and among non-exposed is 1. Right. That is, even if you are not exposed, you will get 1 case. And if you are exposed, you will get 10 cases. So how much extra cases are occurring due to the exposure? 9. And what is the fraction of that among cases who are exposed? It is 9 by 10. That is 90%. This is the easier way that you can do this. So straight away, when you look at this question, you can see that 200 are occurring in 200 cases are occurring in 1,000 smokers, 20 are occurring in 1,000 non-smokers. So it's 10 times higher number of cases. Relative risk is 10, which you can straight away calculate. Okay, so if you get relative risk as 10, you can just imagine that, okay, then it is actually 10 by 1. So attributable risk is 10 minus 1 by 10. That is 9 by 10, 90%. You will get the answer in just 10 seconds if you know what you are doing. Okay, it's clear, right? See, those of you are just confused with what I have written here, just missed 1, 2 zeros here, that's all. And non-exposed is 20 by 1,000. So here, what will happen is 180 by 1,000 divided by 200 by 1,000. That is 90%. So just ignore this part. This is just for you to see if you can't hear me. If you can hear me, just hear me, even no need to read what I have written. Okay, we'll move on to the third question. In a small town of population 10,000, prevalence of alcohol use was estimated to be 30%. Study was done with a null hypothesis that there is no association between alcohol use and gastroesophageal reflux disease. Of the 200 alcoholics who were followed up, 30 developed GERD, and out of 400 non-alcoholics, 30 developed GERD. What fraction of GERD can be prevented in the general population if alcohol is no longer consumed in this town? So they are actually asking you about the population attributable risk. Right. So in this question, the last question, you were given the prevalence of smoking, and you were told that the examiner or the investigator calculated all possible risk measures. So it have also calculated the population attributable risk there, but that was not asked in the question, so it went unanswered also or undiscussed. But here they are asking about that. So what is population attributable risk? I told you that incidence among exposed by incidence among non-exposed is your relative risk, and incidence among exposed minus incidence among non-exposed is your attributable risk, and your attributable risk proportion or attributable risk fraction is incidence among exposed minus incidence among non-exposed by incidence among exposed. This is expressed as a proportion or percentage of incidence among exposed. Population attributable risk is actually that is also another MCQ which tells you if this exposure is removed from the population, what proportion of cases will be decreased in the population, or we can decrease in the population by removing this risk factor. Why is that different from this? Because attributable risk fraction, we are actually seeing how much is contributed in incidence among exposed. Among incidence among exposed, what proportion is due to this exposure? But when we talk about general population, we want to know population.
അറിയാതെ എണീറ്റ് തന്നെ നേരത്തെ എണീറ്റ് ഞാൻ വന്ന് മിൽക്ക് കൊടുത്തു കണ്ണടഞ്ഞടഞ്ഞ് പിന്നെയും ഉറങ്ങാൻ വേണ്ടി ശ്രമിച്ചപ്പോ ഞാൻ എല്ലാവരും
mute, somebody is talking. Okay, so in incidents among if we are when we are actually dealing with a population, then population is a group or a mixture of people who are exposed, who are not exposed, and all. So the exposure is very rare. Then in general population, even if we take away the exposure, the number of cases that we can lower will also be rare because the disease itself will be rare. For example, if we take a cancer, which is rare, which is due to smoking, if there are only 10 cases totally in an year, and even if 9 out of that is due to smoking, even if we take off smoking as an exposure risk factor from the population, we are only going to lower the number of cancers by 9. It is 9 individuals. Fine. But if it is, we are talking now about say smoking and MI, then MI, the number is huge. So even if only say 40 to 50% of the MI is due to smoking, we take away smoking, if there are actually 1,000 myocardial infarctions, just by taking away smoking, we can take off 50% of myocardial infarction. But that will be actually, because there are 1,000 MI, we can reduce it by 500 MIs. So the impact that is happening in the population is huge, even if the attributable risk is low. That depends on how rare the disease is in the population, how many people are affected. So this is often asked as an MCQ in different ways. That is, they might be asking you, if the disease is rare, then attributable risk 90% is, say, will not produce much impact in the population, is the answer. Even if the disease is very common, even an attributable risk of 40 to 50% is there, the population attributable risk will actually be a high value. So we will see how it is being done. The fraction of GERD that can be prevented in the general population if alcohol is no longer consumed in the town is given by the population attributable risk of alcohol in causing GERD. So it is calculated as incidence of GERD in the population minus incidence of GERD among non-alcoholics divided by incidence of GERD in the population. So here we only look at the incidence in the population. We don't look at incidence in the exposed. Incidence in the population minus incidence of GERD among non-alcoholics divided by, that is, we just replace the incidence among exposed by incidence in the population. So from the given data, we can calculate the incidence of GERD in the alcoholic group as 30 by 200 and non-alcoholic group as 30 by 400. Then we can find out the incidence in the population. We know prevalence of alcohol is 30%. So 3,000 people use alcohol. So in them, the incidence would be 30 by 200 into 3,000 is equal to 450. So in the remaining 7,000 people, the incidence would be 30 by 400 into 7,000 is equal to 525. Fine, because we were given that 30% use alcohol. So this 30% will have an incidence of 30 by 200 and the remaining 70% will have the incidence of 30 by 400. So we will get the incidence in the population as 450 plus 525 by 10,000 is equal to 975 by 10,000. It can be expressed at 39 by 400. What is the incidence we are getting in the population? Okay, so 30 by 400 is in the non-exposed and 30 by 200 you can think of it as 60 by 400. So among people who use alcohol, incidence is 60 by 400. Non-alcohol incidence is 30 by 400. And when we calculate the incidence in the general population, which is a mixture of alcoholics and non-alcoholics, the incidence is 39 by 400. So now we know what to do. 39 by 400 minus 30 by 400 divided by 39 by 400 is equal to 9 by 39. Now when we look at the options, option A is same as 9 by 39, which is 45 by 190. Is this clear? So you can expect a question on population attributables that is actually telling you what difference we are going to make in the population when we take off this exposure from the population. When we actually address this issue of smoking, that is, if the address of smoking is totally, if the issue of smoking is totally addressed, and if there is no smoking in the population, how much should the lung cancer decrease? In the same way here, if alcohol is totally taken away from the population, no, there are no alcoholics at all, then what is the difference we are going to make in GER? Is this clear? You can type in if you, yes, yes. Shall I move on? Yes, okay. So, the association between smoking and dementia was proposed as a hypothesis by a researcher. During literature review, he found out that it might require more than 20 years of follow-up to arrive at valid conclusions. He wanted to finish the study within 1 year, but he was not ready to sacrifice the temporality of exposure and outcome. Assuming there were no other feasibility issues, which study design would best suit his requirements? Yes, you can type in your answers. There are 3-4 keywords in the question. Pay attention to all keywords. And yes, I am getting E, C. Okay, people are divided between C and E. No other options. Okay, we'll see. So, before going to answer this question, I will tell you the premise of how this is done. So, which are the basic study designs that you know? And how do we reach our answer? So, two things that I will tell you. So, basically, did investigator assign the exposure? That is the first thing we have to ask. That is, we know that observational is there, experimental is there. Then under observational, we have analytical and descriptive and all. So I am telling you how to answer the question. I am not telling you the full theory, but how to answer this question or any such related questions. First question you have to ask is, did investigator assign the exposure? Yes, then it's an experimental study. If investigator did not, he is only observing, then it is observational study. That is, if investigator has given a drug, then it has become an experimental study. It will no longer be an observational study. Then, if experimental study, investigator has given the exposure, then the next question we ask is there a random allocation, randomization? If there is a randomization, then it is a randomized control trial. There is no randomization, then it is a non-randomized control trial. It will still be called a clinical trial. Now, if the investigator has not assigned the exposure, then it is an observational study. The observational study, then the next question that we should ask is there a comparison group? That is the most important question. If there is no comparison group, then it's a descriptive study. If there is a comparison group, then it's an analytical study. If there is a comparison group, then we look at the direction of the study. Is the study starting with exposure and proceeding to outcome, or is the study starting with outcome and proceeding to exposure? Or are we studying a group where exposure and outcome has occurred and we are just looking at a cross-section to see the prevalence of a disease? If we are just doing a cross section to see the prevalence of a disease, then it's a cross sectional study. So the prevalence is calculated by dash design. The answer is cross sectional study. If we are having now two groups, the two groups which differ according to their outcomes, that is a group with the disease and a group without the disease, and we are asking them few questions to get data about their exposures, and we are doing an analysis, then we are doing a case control study. The two groups in a case control study are cases and controls. Cases are those people with disease and controls are those without the disease. Now, we are starting with two groups. One group is having the exposure and another group is not having the exposure, and we are following these two groups in time, and we are seeing how many of them are developing disease over time after the follow-up. Then we are doing a cohort study. This is clear, right? Okay, so this part is clear, right? Shall I move to the next step? Are there any doubts in this chart? No. Okay. Okay, so the next step is actually, after reading this, do you want to change your answer now? Or do you get the answer from this chart? This is the basic chart. So the points that we got from this chart is, if it is exposure to outcome, it is a cohort study. And if it is outcome to exposure, then it's a case control study. Okay, so what is here in this question? The question, what are the keywords in the question? Association between smoking and dementia has to be found out. But he found out that it might require more than 20 years of follow-up to arrive at the valid conclusions, and this guy only had 1 year with me. So a proper cohort study is not possible, because a 20 years follow-up is required with exposed and unexposed groups to get the outcome. He wanted to finish the study within 1 year, but he was not ready to sacrifice the temporality of exposure and outcome. Now, what does that mean? What is temporality of exposure and outcome? That is, he has to make sure that the outcome is happening only after the exposure in time. So temporality means the time component of the research. Temporality. In science, we have to actually say, കോഴിയാണ് വന്നത്, അത് കഴിഞ്ഞ് കോഴിയാണ് മുട്ട ഇട്ടത് എന്ന് കാണിക്കണം നമുക്ക്. അപ്പോൾ ഈ കേസിൽ നമുക്ക് നമ്മുടെ കയ്യിൽ ആൾക്കാരുള്ള സമയത്ത് they don't have dementia എന്ന് we have to prove. Then നമുക്ക് അതിന് ശേഷം ആണ് നമുക്ക് സ്മോക്കിംഗ് മാത്രമേ ഉള്ളൂ, സ്മോക്കിംഗ് നോൺ സ്മോക്കിംഗ് ആയിട്ട് 2 ഗ്രൂപ്പാണ്. നമ്മുടെ കയ്യിൽ കിട്ടിയതിന് ശേഷമാണ് ഇവർ ഡിമെൻഷ്യ ഡെവലപ്പ് ചെയ്തത്. സ്മോക്കിംഗ് ആണ് ആദ്യം ഉണ്ടായത്, അത് കഴിഞ്ഞാണ് ഡിമെൻഷ്യ വന്നത് എന്ന് പ്രൂവ് ചെയ്താൽ മാത്രമേ നമുക്ക് ടെമ്പറാലിറ്റി കീപ്പ് ചെയ്യാൻ പറ്റുള്ളൂ. In that case, if we go for a case control study, what will happen? Case control study, we take a group with dementia and a group without dementia, and we ask them for the history of smoking. So they already developed dementia by the time they have reached our hand, or say the researcher's office. So we will not be able to say whether dementia occurred first or smoking occurred first. If somebody tells you that they started smoking only 2 years back, you will not be sure whether they had dementia even before 2 years. So the temporality is compromised. So if he is not ready to sacrifice the temporality of exposure and outcome, a case control study design is not possible. Okay. Then they are telling there are no other feasibility issues. Now, what is a case cohort study design or what is a nested case control study design? If it is new to you, a case cohort study design or a nested case control study design is when we actually have a cohort in hand, we follow up the cohort, and when there are cases developing in the cohort, we recruit them to the case group and we take few controls and we do a case control analysis in that cohort. That is a case control study is nested inside a cohort study. But as we know, if you are developing a cohort for this and following them up, it will all take years for the cases to develop and the controls to be selected. The controls are selected right when the cases are identified in a nested case control study, and the case cohort study that in the sense that the controls are selected after we get all the cases. That is the difference between B and E. In both cases, we need a cohort group and follow the group and wait for the cases to develop. So because 20 years is there to follow up, both case control, case cohort and nested case control are not possible here because this guy has only got 1 year with him. What is case crossover study design? Here the cases are crossed over to the control side to see that they have this outcome during exposure or a period during non-exposure. So this can be applicable only to acute cases. That is, they will be in a exposed group for say a fixed amount of time. Then they will be crossed over to the unexposed group for a fixed amount of time. And the outcomes will be measured in both the durations. So that is also not the answer. Then what is the answer? Only one is left, retrospective cohort study design. So what is retrospective cohort study? Retrospective cohort study is a cohort study, but what we do there is we go back in time and we assemble the exposed and unexposed groups in some historical period using records. So here they have told us there are no other feasibility issues. That means records are available. Even if we ask for records, it is available. There are no feasibility issues for conducting this study. So we go back in time and say 20 years is the time for developing this thing. We actually go back maybe to 1980 or 1970 as far as the records are available in the past. Or say we can go back up to 2000, goes to 2022. And we identify smokers and non-smokers through records and we assemble a cohort in the records. Then we get those cases now. We consider they have been followed up through the records. If there are annual checkups every year and all, there will be the status will be given. If they develop dementia, it will also be recorded in the records and all. So we follow up through the records and now already 20 years have elapsed. So we might get the outcome now. It is just your cohort study, which is taken from the current day and just moved a bit back into the history so that exposure happened some 20 years back through records. We are following that up and outcome is happening now. So we cannot compromise or in temporality with this design. That is because it's a cohort study. We are going back in time and assembling the, because then 20 years back, if you take someone, the records will clearly say that that guy is totally healthy. There are no signs of dementia, any other disease, or he is a smoker and there are no other issues. So that is enough evidence to say that smoking has started since then, but there were no signs of any other disease. And only after following him for say 15 years, only 5 years back, he showed signs of dementia. Then we can say that through records, the follow-up is being perfect and the patient only developed dementia 5 years back and so temporality is intact. Fine. So that is retrospective study design. So it will be like your case control study, but the difference is in case control study, the two groups are cases and controls, and we look back in the history to get the exposure data. But in retrospective cohort, we go back to the history and assemble the two groups based on exposure and not based on outcome from the record of exposures in the past, and we measure the outcome now. Is this question clear? Yeah. Case cohort and a nested case control study both are a case control study which is nested inside a cohort study. That is, there will be a big cohort study and there will be a small case control study that is nested inside that big cohort study. And nested in the sense that the big cohort acts like a nest for this small study, like a bird who is living in a big nest. Okay, so the difference is we are following up that big cohort and there will be some cases. That is, say for example, the same example, we are having this cohort for 20-25 years. Some people now and then develop dementia. So we recruit them to a case group. That is, everything is happened within that big cohort. Everything is happening within that big cohort. That is the point. Okay, so we will get say 10-20 dementia cases within that big cohort. It forms our case group. Now, in a nested case control study, when one case of dementia is being identified, we take one control also from this cohort along with that case, because it's a control for the same period of time as exposure, because exposures would be same, no, for both, for ensuring that. And say after 2 years another dementia is developing, we take another control along with that case. If you are identifying the controls like that along with every single case, by the time we are having say around 25 dementia cases, we will be having 25 controls also, which were identified along with these cases or at the time of the diagnosis of these cases. Control would be someone in the same cohort who did not develop dementia, that's all. Like that, if you are doing a case control analysis in these patients, then that is a nested case control design. A case cohort design is when we identify all the 25 dementia cases. After identifying 25 dementia cases, then we take 25 controls from the big cohort itself. That is, the controls are taken together at the end of the identification of cases. Then that will become a case cohort study design. Both are basically called hybrid designs. That is also another MCQ. Hybrid design. That is a design when we are combining 2 or 3 known designs to get designs like this. Okay. So another question now, this you can answer straight away because I have already explained everything. The researcher wanted to study about the carcinogenic effects of a food additive. From the literature, he found out that around 7 different types of cancer were suspected to occur due to the consumption of this food additive. He wanted to study all the possible 7 outcomes. He conducted interviews with a couple of his potential study subjects and discovered that the awareness about this food additive was very low among them, though they were consuming it regularly through various foods. Which study design would be best suit this research? Yes, what is your answer? That is, he wanted to study about the question is, which study design would best suit this research? Actually, you can do the study in A using A, B, or C, or D, or E in different situations and circumstances. But due to many different factors, only one design would be best suited and all others would not be feasible. Okay. We'll see. A cohort design is best to study a single exposure leading to multiple outcomes. Why? Now you can think. There is a single exposure leading to multiple outcomes. It is best, the easiest way is to have a group that is exposed and have a group that is not exposed, follow them up and to see whether they are developing any issues. But there would be many feasibility issues also. Like the follow-up period would be high or low and all. In this question, they have not told you about any time constraints. Like the earlier question, they have not told you about time constraints. They have only told you about which design would suit best. So you can go for the best design. Choice A, if a case control study would be very difficult as outcomes are multiple here. So for each outcome, you have to take a disease group, a case group and a control group. A case control study is best suited to study a single outcome with multiple risk factors. That is another MCQ. To study multiple risk factors, which design is best suited. Always say case control study because we take a group of cases and controls and we look back to identify the risk factors there. So even if there are 5 to 10 risk factors, one group with the disease and another group without the disease can tell you. In this case, there is one exposure and multiple outcomes. In that case, if time constraint is not there, then we will always go for a cohort study. Okay. If records are intact and there is no cohort study in the option, you can also go for retrospective cohort. But we know that this is a new thing and the even awareness is less about this thing. So it will be difficult to get records for this thing logically. But you might have it. If they are told you that there are no other feasibility issues and all, then maybe records would be there. So look at every scenario in the question and every sentence clearly and every word clearly to reach the best answer. Choice C. In this case, people are not aware of this food additive, and as it would be near impossible to get records for such data, we cannot do a retrospective cohort design here. Choice D. Randomized clinical trial will have ethical issues in this case. As the outcome is a serious disease in this case, theoretically, randomized control trial can be done, but practically not. That point is very, very important. Many of the cases, or say case control studies or cohort studies, would be best done in a randomized control trial way, where we can absolutely be sure about the exposure and outcome. But it is not at all possible due to ethical issues. The outcome is a disease or a rather serious disease. We cannot knowingly give someone an exposure that can create a fatal outcome. So we cannot do RCT in most of the situations, even if theoretically that is the best answer. So when they are asking you for the best design, you cannot ignore the ethical issues. You can ignore the time constraints or the amount constraints and all, because we have to do cohort studies in many cases, even if there are time constraints, because the best data is got from the cohort studies. If records are not there, only cohort study can give you a temporal data. Okay. But ethical issues you cannot ignore in any situations. So we see cross-sectional study can be done to study the prevalence and proportions, but to study associations, we need analytical study designs, control groups. Clear? So we will move to the next question. Is it clear? Designs. This is also about the designs. A new drug A, which passed safety and efficacy test, was now going to be tested against a drug B for comparison purposes. The doctor who was conducting this study recruited 380 individuals who were willing to participate in the study. He divided them into 2 groups of 190 each, and he didn't inform any of the patients which drug they were getting. So he was aware of it while giving them the drugs. After the study period, data was analyzed and results were obtained. The study design was used here. Yes. Read every word in the question clearly. I repeat it again and again. Go back to my chart of identifying study designs. The investigator assigned the exposure. Yes, so it's experimental study. Was random allocation done? No, exactly. Some of you have answered it correctly. Random allocation was not done. There is no randomization. So it's not a randomized control trial. It is not a case control study design. It is not a cohort design. It is not a case crossover study design. Because why? Because it's an experimental design, not an observational design. So only two experimental designs are here. One is randomized clinical trial design and other is clinical trial design. So randomized clinical trial design and non-randomized clinical trial designs are together called as clinical trial design. So this is a non-RCT, but because non-RCT is not in the choice, clinical trial design is the answer. Okay, so look at the question and see whether randomization has been talked about. If it is not talked about, then it is a non-RCT. Fine. This is a clinical trial design and not a randomized clinical trial design because a randomization has not been done. People were not told which group they belong to, and that means a blinding was done. That is another MCQ. What is blinding? Single blinding, double blinding, and triple blinding. So blinding is done when the patient does not know. A single blinding, the patient does not know what treatment he is getting. Double blinding, the investigator also does not know. In triple blinding, the one who is doing the analysis will also be unaware of who is who. Okay, so what is blinding helping us with? Randomization is helping us with what? Randomization is helping us with the selection bias. Because randomization divides the people into two groups clearly. Randomization ensures that every individual ends up in a study group or the control group randomly. So randomization helps us in better comparison of the two groups as the unknown confounders would be somewhat equally distributed. Very, very important MCQ. Randomization, we have many methods to adjust the non-confounders, such as matching, restriction. You already know that. Matching, restriction, stratification, regression, and also stratification and regression are done during the analysis stage. Matching, restriction, and randomization are done during the selection allocation stage and all. So here, randomization is the only thing which takes care of the unknown confounders also. The others can be applied only to the non-confound. The other things that we do during the selection process, matching and restriction can be only applied to non-confounders. So to address unknown confounders, what is the method? Randomization. So randomization is helping us to avoid selection bias. Blinding is actually helping us to avoid measurement bias or the information bias, basically. Because the patient will not give you wrong data because he does not know what he has been assigned to. The doctor will not make a mistake because he also doesn't know what he is seeing, whether the patient is taking the drug or not. Somebody said interviewer bias, that all comes in the information bias. Bias are basically divided into three: selection, information, and confounding. Selection, this information bias is somewhat also called misclassification bias. Basically, three types: selection, information, and confounding. Blinding comes in the second group, and selection comes in the first group. Choice B, here it is specified that the intervention is given by the researcher himself, so this becomes a trial and not an observational study. So cohort case count all ruled out. Case crossover we already discussed is where the cases serve as their own controls. Exposure during the time period just before the outcome is compared with an earlier time period when the outcome did not occur. That is, the cases will act as their own controls in a different time period. So don't confuse this case crossover study with a crossover RCT. Crossover RCT is also an experimental design. Case crossover study will be basically an observational design. Okay, that will be called crossover RCT. That's all. So we'll move to the next question. So design part we have covered as much as possible in the short period. This is a bit of statistics and epidemiology combined in this question. The frequencies of different hemoglobin levels of all 1,000 medical students in a college were plotted in a graph. The distribution curve was obtained. The mean was 11.2 gram per deciliter with a standard deviation of 2.1. The median was 11.1 gram per deciliter and mode was 11.3 gram per deciliter. It was decided that all students having hemoglobin level below 7 gram per deciliter would be referred to a nearby hematology clinic for expert evaluation and management. Approximately how many students would have been referred? Yes, how do we do this? What is your answer? If you know how to do this, you can type in the answer. And if you have some idea about how to do this, you can type in your idea also, so that I know what you know. And I know how much to explain. So that I know how much to explain. Yes. If you have no idea, just type in no idea. Then I'll explain it totally. Okay. So I'll explain from the beginning. Yeah, somebody has the answer. Very good. Excellent. Okay. I think another person has also got the answer, but just a single step went wrong. One person is right. So how do we approach this question? This question is basically about the normal distribution. This is the normal distribution curve. Right? So you have to learn this in and out, because so many questions in different ways can be asked from this one diagram. So here, this is a normal distribution. In normal distribution, mean, mode, and median will coincide. The question also, you can see that mean, mode, and median are almost same and equal. So you get an idea from that itself that it's a normal distribution. A normal distribution is bilaterally symmetrical. A normal distribution is asymptotic, which means that the two ends will not touch the base. What you are seeing here is a standard normal distribution. That is why it is touching the base. Standard normal distribution is what we draw from a normal distribution, where we make the mean 0 and standard deviation 1. Just to interpret and express clearly. So standard normal distribution is something that we make from a normal distribution with mean as 0 and standard deviation as 1, as you can see in this diagram. In a normal distribution, mean will not be 0, but mean, mode, and median, mean, median, and mode will be same. Okay, standard deviation will not be 1; it will be the actual value. And a normal distribution is asymptotic; that is, it will not touch the baseline. So, as it does not touch the baseline, we cannot calculate the area under the curve also. In a standard normal distribution, area under the curve is 1. That is another MCQ. They will ask you area under the curve is 1 in, and there will be a choice, there will be normal distribution also, and maybe there will be none of the above. The answer is none of the above. There is no standard normal distribution here among the choices. For a normal distribution, area under the curve is not 1 because it does not touch the baseline, so we cannot calculate the area under the curve. That is called asymptotic nature. Now, in a normal distribution as well as in a standard normal distribution, mean plus or minus 1 standard deviation will have 68.3% of the values. That is, now coming back to the question, hemoglobin value of 1000 students. So our N is equal to 1000. Mean is 11.2. What is standard deviation? 2.1. So one standard deviation is 2.1. So 11.2 plus or minus 2.1. How much is that? 13.3 is the upper limit, and 11.2 minus 2.1. That is 9.1. So between 9.1 and 13.3, there will be 68.3% of the students. That is, total is 1000. So 683 will lie between one standard deviation. That is 9.1 and 13.3. How much is 2 standard deviation? 2.1 into 2, that is 4.2. 11.2 minus 4.2 is 7. 11.2 plus 4.2 is 15.4. So between 7 and 15.4, 954 students will lie, or say 95.4% students will lie. And between 3 standard deviations, there will be, this between 3 means between plus or minus 3 SD. That is between minus 3 SD and plus 3 SD. 99.7% of students, whereas 997 students will lie. Is that clear? Now from the second possibility, we got that 954 students are lying between 7 and 15.4. That is 2 standard deviations. Because this is bilaterally symmetrical, half will lie on one side of the mean and half will lie on other side of the mean. That is, the central line is the mean here. So of this 954, we know that half of it, that is 427, not 427, 477, right? Half of that. 470. How much is that? 954 by 2. Somebody type in. I think my brain is not working properly. So 954 by 2, 960 by 2 is 480. So it will be 477, right? So that much number will lie in one side of the mean and same will lie in other side of the mean. So now what? Now we know that because 954 is lying between or within the 2 SDs on both sides, the remaining 46 are lying beyond this 2 standard deviation. It can be on either side. So how many are lying on either side? Of 46 in total. So this 46 in total are lying either on the negative side, that is less than 7, or on the higher side, that is higher than 15.4. So how many will be less than 7? Half of that, because it is bilaterally symmetrical. So 46 by 2, that is 23. So 23 will be there in less than 7 group. And look at the choices. Only nearby thing is 25, and they've asked you only approximately how many students to make arrangements for them. So we can say approximately 25 students will be there. Is this clear? So this can be asked in many different ways. Just remember, 68.3% will lie between the mean and 1 standard deviations on either side, plus or minus 1 SD. 2 standard deviations, 95.4%. 3 standard deviations and 9.7%. Okay, the last part is we got mean plus or minus 2 SD will contain 954 students. That is clear, right? SS90, till that is clear, right? Mean plus or minus 2 standard deviations will contain 954 students. So the remaining of 46 students out of the 1000 students are lying either less than 2 standard deviations or higher than 2 standard deviations. That is mean plus or minus 2 SD part, we have 954 students. The remaining 46 are lying either below that or above that. Because it is bilaterally symmetrical, how much is left? We can just divide it by 2 and we can say that half of the 46 is less than 7 and half of the 46 is higher than 15.2. 7 being the 2 SD line, minus 2 SD line, and 15.4 being the plus 2 SD line. So 23 are less than 7 and 23 are greater than 15.4. So they have only asked us how many will be referred with anemia, less than 7 to the hospital, roughly 25. Okay, so we move on to the next question. The researcher faced a task of calculating the mean height of male students in a college having 2000 male students and 1750 female students. The mean height of the sample was obtained as 176 centimeters with a standard deviation of 7 centimeters. The researcher calculated a confidence interval for the mean height of the male students in that college. What more do you need to calculate? The same. Same question asked in a twisted way. So researcher faced a task of calculating the mean height of male students in a college having 2000 male students and 1750 female students. The mean height of the sample was obtained as 176 centimeters. The height of sample was obtained, it was 176 centimeters with a standard deviation of 7 centimeters. They are asking you, what more do you need? So you have to read every word in the question actually. I'll explain this because we don't have much time. Here we need to calculate the confidence interval for the mean height of the male students in that college. We have a sample statistic, which is the mean height of our sample and the standard deviation of our sample. The confidence interval for the mean height of the male students is given by mean height plus or minus 1.96 SC. Right. It's actually 2 SC. It's exactly 1.96 SC. Where SC is the standard error of the mean. Standard error term is given by dividing the standard deviation by square root of sample size. SD by root n. We already discussed this in the last class. So we need to know the sample size of the study, which is not mentioned in the question. That is, they given us the sample value, but they have not given us the sample size. So if you know the sample size, then you can calculate the SC from that. The mean height of the male students in that college is called the population parameter, which can be found out only if we measure all the 2000 male students and found out its mean, which would be very tedious, and that is why we resort to sampling. Choice B, total number of non-participants in our sample is what we are concerned about, and it is not a problem as long as we ensure that the sample is representative. Okay. What was the choice B? Total number of male students in that college who did not take part in the study. We don't want that. We have a sample now. A sampling frame of all the students in the college helps us in selecting a random sample, but it does not provide a sample size or help us in calculating the confidence interval. Choice D was sampling frame. Even if we get that, it will help us in selecting a random sample. The question is here, we have a sample value, but they have not told us about the sample size. So if we get the sample size of the study, we can calculate we have the standard deviations. We can calculate the standard error using SD by root n. And once we get the standard error, we can calculate the confidence interval easily by using the formula mean height plus or minus 1.96 SC. We have the mean height already. Okay, this is the application question that you can get from standard error, standard deviation, and all. So just remember this much: standard error is actually standard deviation divided by root n, where n is a sample size, and the confidence interval is mean plus or minus 2 standard errors. It's exactly 1.96, but often rounded off as 2. If both 2 and 1.96 are there in the question, 1.96 is the answer. Okay, moving on to the next question. It's getting a bit more difficult. A doctor arrived at a hypothesis that low birth weight is related with obesity in later life. He conducted a study at 95% confidence significance level to disprove his null hypothesis, and he got a p-value of 0.049. He rejected a null hypothesis and concluded that low birth weight is associated with obesity. In this study, he didn't commit a type 1 error. He cannot commit a type 2 error. He should not have rejected a null hypothesis. 90% significance level should have been kept. He committed a type 2 error. What is the answer? Are you clear with this alpha error, beta error, and all? To teach alpha error and beta error, it will take like 20 minutes. To already know it, I can just explain in just 2-3 minutes. Okay, I will just explain a bit. I think our time is very short for full explanations. So this is the basic graph that you have to see. When your confidence limit is say 95%, the allowable alpha error is 5%. So you have a hypothesis, null hypothesis to start with, which is true or false. In reality, it is a null hypothesis that you frame can either be true or false in reality. And the decision from your part would be to reject your null hypothesis or to accept null hypothesis. That is, you do not reject it. Accept is not a good word to be used here. You either reject or do not reject, but it's there just for explanation's sake. So decision is whether to accept it or not, or reject it or not. Okay. The hypothesis would be in reality true or false. So if the hypothesis in reality is true and you accept it, it's a right decision. But the hypothesis is true, but you reject it, you are actually making an alpha error or a type 1 error, which is also called a grave error. That means if there is a drug which is actually good, it can be given. There is a drug which is actually not good, it should not be given. Right. The hypothesis, null hypothesis in the case when you are doing research with this drug would be this drug is not effective, or there is no difference between this drug and the placebo. If that is true, then it should not be rejected, right? If that is false, it should be rejected. So if that is true, we do not reject it, it's a right decision. That is the initial cell A is right. But if you're rejecting that null hypothesis after the study, based on your p-value, and in reality, if that hypothesis is actually true, that is, a drug is not that effective, then it's a very big mistake because you are going to give that drug to the patients. Okay, so that error should not be committed. It's a type 1 error. So science has told us that the maximum allowable alpha of 5%. You cannot go beyond 5%. That is, you can reject a null hypothesis even when it is true, but only up to 5%. This alpha error up to 5% is acceptable by the scientific community. because alpha error up to 5% is acceptable, that is why your p-value is at 0.05. So anything less than 0.05 in a p-value means you are going to commit an alpha error less than 5%, which is acceptable. That is why we say if the p-value is less than 0.05, we can reject the null hypothesis, because even if we are making an alpha error by rejecting the null hypothesis, we are going to commit an alpha error only less than 5%. This is acceptable. Beta error is the other part of it. That is, when the actual null hypothesis is false, we have this decision of beta error rejecting the beta. We have this decision of rejecting null hypothesis, right? When we reject null hypothesis when it is false, it's a right decision. That is the last cell or the D column. But what happens in the C column? We are not rejecting a null hypothesis even when it is false. That is, null hypothesis of false means what null hypothesis was, the drug is not effective. It is false means the drug is actually good. Okay, but we are not rejecting the null hypothesis and we are accepting the null hypothesis, which says that the drug is not effective. So we are not making use of a good drug, saying that the drug is not effective. So a good drug is lost. That is a beta error. That is a type 2 error. And scientific community has told us that beta can be up to 20%. So I told you beta error is when we do not reject null hypothesis when it is false. Drug is good, but we did not reject null hypothesis and said that null hypothesis is true. That is, the drug is not effective. That's so our study was not able to pick up the efficacy of the drug. That is the beta error. So what is now 1 minus beta? If beta error is the inability of our study to pick up the efficiency of or efficacy of that drug, then 1 minus beta is actually the ability of our study to identify the efficacy of that drug. So that is why 1 minus beta is called power of the study. It is another MCQ. Power of the study is 1 minus beta. So I have only done, say, a superficial explanation of this due to lack of time. Because 1.5 hours, each MCQ you are only getting 5 minutes maximum. This is the best I can do in 5 minutes. To teach this is actually an hour of lecture in detail. So I hope you understood this. MCQ point of view, what we need to know is rejecting null hypothesis when it is true is an alpha error. Not rejecting null hypothesis when it is false is a type 2 error or the beta error. Alpha can be maximum up to 5%, beta can be maximum up to 20%. Because alpha is fixed at 5%, the p-value is often we take it as less than 0.05. So p-value is actually the probability of a finding to occur when null hypothesis is true. It is a condition of a p-value. P-value is a conditional probability where we say that if null hypothesis is true, what is the probability of the finding that we get in the study to be there? Okay, that is, if the drug is not effective, if it is the drug is for lowering the BP, if the drug is not effective, which is null hypothesis, if that hypothesis, null hypothesis is true, then what is the probability of seeing this difference in the BP? Okay, that is the p-value. So if p-value is very, very low, p-value is less than 0.05, and say if a p-value is 0.03, then that means that if the null hypothesis is true, that is, if the drug is not effective, the probability of seeing this difference is only 3%. Okay. So we reject it because even if that is wrong, if that is wrong means an alpha error. Even if that is wrong, then this alpha error is only 3%, which is less than 5, which is the acceptable limit. That is why if we get p-value of less than 0.5, we reject it. If we are doing a study with a 95% level of significance, that is arbitrary. If we want a level of significance of 99%, then alpha error allowable would be 1. And p-value cutoff would be 0.01. That we can change according to the study, but it should not be above 5 in any case, and a p-value of higher than 0.05 is not acceptable in any case. So maximum limit is 0.05 for the p-value and 5% for the alpha. You can just imagine yourself in a court of law for the comparison here. Null hypothesis is the judge is saying the victim is innocent or the victim has got nothing to do with the crime. Oh, victim means the person who is there inside the case. Okay, or the person, say, accused, so that victim may be someone who is dead or being robbed and all. To avoid their confusion, actually meant the victim of the law, but just say accused for it to be clear. Accused is innocent, is where the judge starts with a null hypothesis. Then the advocate gives him evidence. The judge thinks, if this guy is innocent, what is the probability of this evidence to be right? So with just one simple evidence, if the judge says that he is guilty, judge is committing an nullifier because he is going to punish an innocent. So judge needs to be totally sure that his alpha is very, very low, that the p-value is very, very low. Okay, with each evidence, the p-value improves. Maybe it starts from 0.5 and it improves and goes to say 0.001. Now, even if the judge says that null hypothesis is wrong, that is the accused is not innocent and sentences him to death, then the alpha error is very negligible because he has got all the evidence which actually now puts the alpha in an abysmally low levels. But in science, we don't go to that level. We are happy with 5%. Okay, I think this is very difficult, this part. You can read off your own. This is the maximum time I can spend on this question as per our schedule. I hope it is clear. So what is the answer now? A type 1 error or alpha error occurs when a true null hypothesis is rejected. That is, we say there is a difference when actually there is no difference. Type 2 error or beta error occurs when a false null hypothesis is not rejected. That is, we say there is no difference when actually there is a difference. This occurs when our study is not able to bring out the true difference. Hence, 1 minus beta is called power of the study, which is the ability of our study to bring out the true difference. This is the gist of what I said. So if we see the above two statements, it is clear that a type 1 error occurs only when we reject a null hypothesis, and a type 2 error occurs only when we do not reject the null hypothesis. This is the point for our answer. Hence, doctor in our question cannot commit a type 2 error as he has already rejected his null hypothesis. He is only at risk of committing a type 1 error. He was right in rejecting null hypothesis as he got a significant p-value with his arbitrary 95% significance level. Okay, because that is said. Choice D, at least 95% significance level is recommended for scientific studies. If he wishes, he can do a study at 99% significance level, keeping his p-value level at 0.01, but he should not go below 95%. Below means he cannot go to 93 or 94 and all. He cannot commit a type 2 error as he has already rejected the null hypothesis. Okay, you can look at the question once more to be clear. A doctor arrived at a hypothesis that low birth weight is related with obesity. He conducted a study at 95% significant level, disposed null hypothesis, and he got a p-value of 0.049, that is less than 0.05. So he rejected null hypothesis. So he can commit a type 1 error here because he has rejected null hypothesis. His p-value is what? 0.049. You can round it off and say 5%. Then there is a 5% chance for him to commit the alpha error. But as 5 is acceptable, allowable alpha error, he is fine. But he can commit a alpha type 1 error or alpha error. Because he has already rejected null hypothesis, he cannot commit a type 2 error. So B is the answer. He should not have rejected null hypothesis. No, he got a significant p-value, so he can reject. 90% significance level should have been kept. No, at least 95 has to be there. He committed a type 2 error. No, because he has already rejected null hypothesis. Because it's already rejected null hypothesis, he cannot commit a type 2 error. Fine. So you have to only know this much in this for the MCQs, but only if you know the entire idea, you can actually get to other MCQs which are twisted a bit. But I don't think that you will be asked too complicated ones from this part. Only remember this part. Alpha error is committed when a true hypothesis is rejected. That is when a hypothesis is rejected. An hypothesis is rejected when it is true. And beta is committed when it is not rejected, even when it is false. And the other things that I explained now. Next question. You can speed up now because we already discussed all these things. Researcher was studying the association between hemoglobin value and BMI. He divided the two students into class into two groups based on their BMIs into normal weight group and overweight group. Then he measured the hemoglobin values of all the students. His null hypothesis was there is no association between hemoglobin value and the body weight. The mean hemoglobin value of the normal weight group was 13.4 and that of the overweight group was 13.8. He obtained a mean difference of 0.4 gram per deciliter between the two groups. He did an unpaired t-test and he got a p-value of 0.10. What does this mean? What does this mean? I'll explain this. So we know we used a t-test. Fine. So when do we use a t-test? Remember this table from the last class? When one variable is qualitative, other variable is quantitative, we use t-test when there are only two groups for the qualitative or the categorical variable and the quantitative variable is normally distributed. There are more than two groups, we use ANOVA. Or if the quantitative variable is non-normally distributed, we go for non-parametric tests. So the non-parametric test we will explain later. If both variables are qualitative, we go for a chi-square. If both variables are quantitative, we go for correlation. It could be parametric correlation or non-parametric correlation. This is the basis. So here, which are the two groups? BMI is one group and hemoglobin is other group. So BMI, he took it as normal group and overweight group. So there are two groups basically. That's why he did an unpaired t-test. And he got a p-value of 0.1. Is that significant? No. Less than 0.05 is significant. So we will see the explanation. P-value gives the probability to get a finding or more extreme findings if the null hypothesis is true. Thus, a p-value of 0.10 in this question means that even if there is no association between hemoglobin value and weight, there is a 10% probability of getting a difference of 0.4 due to chance alone. Hence, as it is now, it is not below 5%. We do not reject the null hypothesis because we have arbitrarily set it as 5% level for alpha error. We do not reject it because the alpha error can be up to 10% if we reject it. That is not acceptable. So p-value is not just a probability due to chance, but it is a probability due to chance provided null hypothesis is true. That part can be there in the question. P-value has a meaning only when we take null hypothesis to be true. The 0.05 cutoff is arbitrary and one can take a cutoff of 0.02 or 0.01 depending. Okay. So null hypothesis is not true. 10% or higher of the students still do not show any association between hemoglobin value and weight. If null hypothesis is true, there is 10% probability to get this difference of 0.4 gram per deciliter due to chance. That is the answer. If hypothesis is true, there is still a 10% probability to not to get this difference. Null hypothesis is true, there is a 10% probability not to get this difference of 4. That is all those are just the word gibbles or the word plays with this thing. If you know the right thing, you can just straight away go for that. But read all the choices before you answer. So you can straight away, you know, p-value holds some value or say significance only when null hypothesis is true. We can straight away avoid the choices which says hypothesis is not true. When with true, you can see what else is said about the 10%. So we arrive at that answer. Another similar question, a pre-test questionnaire was given to a group of 67 students to assess their knowledge before a 3-day workshop on undergraduate biostatistics. Students were asked not to write their names or registered numbers on the questionnaire sheet to maintain anonymity while evaluation. Even code numbers were not used. Questionnaires were filled and returned within 10 minutes. After the 3-day workshop, the same questionnaire was again given as post-test. All the post-test questionnaires, later the data entry and analysis was done by a different organizer, and also what test is being used here is the question. It's a pre and post, but there is a twist. So anyone has an answer, or shall I explain? Time is a bit short, so I think I should explain. This is an ideal situation for a IIT, right? Because there are two groups, and two groups, there are no two groups, only one group before and after two situations. One is pre-test and one is post-test. It's an ideal thing for a IIT. But the problem here is questionnaire was anonymous and we don't know whose mark is which for the pre and post. We only have two sets of values here. So for the pair distribution, we need the answers in, or we need the observations in pairs. That is, a pre-test score of individual A should have the pre-test a posted score of individual A along with it as a pair of scores. Only if that data is available, we can do a IIT test. Otherwise, we are left with only one choice of go to an unpaired test. Okay, and they are asked which parametric test would you use? That is why the answer is unpaired test. Wilcoxon sum rank test is another name for Mann-Whitney U test. This is a non-parametric counterpart of an unpaired test. Wilcoxon sign rank test is a non-parametric counterpart of IIT test. Because you can't do a paired T, you can't do Wilcoxon sign rank also. And Friedman's test in the choice is a non-parametric counterpart of your repeated measures ANOVA. You do ANOVA when you have one categorical variable with three groups and a quantitative variable which is normally distributed. If that quantitative variable is not normally distributed, you go to the non-parametric counterpart of ANOVA, which is called a Kruskal-Wallis test. When you have just a single group and you are doing repeated measures on that again and again, 3 measurements, 4 measurements, in that case, we go for repeated measures ANOVA. One parameter counterpart of that is a Friedman's test. I have one table showing all this. I will show you that. I will explain this thing. So, this is that master table. Two related groups normally distributed. You have a paired T, and two unrelated groups. As independent groups, you have unpaired T. And not normally distributed. Two related groups, you have the Wilcoxon sign rank. Two unrelated groups, you have the Mann-Whitney U. And more than two groups, you have different groups. One measurement, you have ANOVA. Different, you have same group, different measurements, or more than two measurements, you repeat measures ANOVA. One parameter counterpart of this is a Kruskal-Wallis and a Friedman's test. If it is qualitative, both qualitative variables, you go for a I-square. This is the basic idea of which test. Qualitative or both qualitative, both quantitative we go for a correlation, both qualitative we go for a I-square. One is qualitative, one is quantitative. The quantitative is normally distributed and the qualitative is having two groups. We go for t-test or unpaired t-test or things ANOVA and all based on number of groups or the non-parametric counterparts of the same. This is only what the time allows me to tell you. This is also another 1 hour class. Okay, so shall we stop here or shall we continue? I have just like now 10 more questions, I think. All these are tough.
നമുക്കിപ്പോ എനിക്ക് തോന്നുന്നു 48 പേരുണ്ട്.
Shall we continue?
48 പേരുണ്ട്.
Yeah, about all the questions in maybe 10-15 minutes. If you want me to explain.
15 minutes. I think it's okay. നമുക്ക് ബാക്കി കുട്ടികളുണ്ട്, 47 പേരുണ്ടല്ലോ. നമുക്ക് എനിക്ക് തോന്നുന്നു ഒരു 15 മിനിറ്റ്സ് കൂടെ എടുക്കാം. അപ്പൊ തീരുമല്ലോ. ഇനിയിപ്പോ നമുക്ക് സെഷൻ കിട്ടില്ല.
Within the time, സമയത്തിന് പറ്റുന്ന പോലെ ഐഡിയ തരാം. Evaluation. ഇങ്ങനെയാണ് usually questions വരുന്നത്. As I earlier told you, because the questions are displayed on a computer screen, if it can be seen on my screen, it can also be there on your screen. So the exam. നമുക്ക് നേരത്തെ ക്വസ്റ്റ്യൻ പേപ്പേഴ്സ് ആയിരുന്നപ്പോ ഷോർട്ട് ആയിരിക്കും ക്വസ്റ്റ്യൻസ്, അല്ലെങ്കിൽ അവർക്ക് ഒരുപാട് സ്ഥലം വേണം അച്ചടിച്ച് വരാന്. ആ പ്രശ്നമില്ല ഇപ്പോ. ഇങ്ങനത്തെ കുറെ ക്വസ്റ്റ്യൻസ് കണ്ടു. ഈസി ആയിരിക്കും, ഒന്ന് വായിച്ചു പോകേണ്ട പാടേ ഉള്ളൂ. ഡയഗ്നോസ്റ്റിക് ന്യൂ ഇമേജിംഗ് മൊഡാലിറ്റി ഫോർ ഡിറ്റക്ടിംഗ് salivary gland tumors. Test picked up 90 positives out of the 100 cases that gave a positive result with a gold standard. Out of the 100 negative results with the gold standard, 80 were said to be negative by the test. It was calculated that of the 110 positive results given by the test, 20 were false positives, whereas only 10 were false negatives. What is the positive likelihood ratio for this test? It's the question. Just leave it here. I will tell you what these are in a very concise way. Basically, this is it. The 2x2 table. You know the ABCD, right? That we drew the other day. True positive is A, false positive is B, false negative is C, and true negative is D. Usually you get it as A by A plus A and all. Here I just use the positive negative to tell you the idea. So the first column tells you about people with the disease, that is they who are sick. Second column, people who are healthy. So TP plus FN, or the true positive plus false negative, is your total number of people with the disease. The false positive plus true negative, that is the second column, is your total number of people who are healthy. Sensitivity is out of those with the disease, how many are identified by the test as positive. That is, you can look at the first column. There are people with the disease. Out of that, the test identified as positive for only this much. How much? So I write here A. It is for you to better understanding this with A and easier to explain. This is C and this is D. So true positive A and false negative C, sensitivity would be A by total number of people with the disease, that is A plus C. A by A plus C. It is out of total number of people with the disease, how many are true positive. False, and what is specificity? It is out of those without the disease, how many were identified by the test as negatives. Okay, that is the people B plus D, the test identified D as a negative. Total number of people who are healthy are B plus D, and total number of people identified and negative by the test is D. The specificity is D by B plus D. Positive predictive value is out of the total positive results you got, how many are true positives. That is TP divided by all positives, or say A by A plus B. You have A plus B positive results after the test. Out of that, how many are truly positive? That is A. That is A by A plus B. The row. Negative predictive value is the second row. That is, out of all the negative results, how many are truly negative? This is a basic thing. And what is positive likelihood ratio? Is the likelihood of a test to be positive in people with the disease divided by likelihood of the test to be positive in people without the disease. People with the disease is A plus C. Out of that, A is true positive. So A by A plus C is the likelihood of the test to be positive in people with the disease divided by likelihood of people to be positive in people without the disease is number of people who are positive in people without the disease or healthy is B by B plus D. So it is actually A by A plus C divided by B by B plus D. Okay. So just think A by A plus C is sensitivity. And what is B by B plus D? B by B, you know, D by B plus D is your specificity. So B by B plus D is your 1 minus specificity. So positive likelihood ratio is sensitivity by 1 minus specificity in formula terms. So positive likelihood ratio is the probability of a person with disease testing positive divided by probability of a person without disease testing positive. In terms of sensitivity and specificity expressed as sensitivity by 1 minus specificity. This could be asked for your exams. Sensitivity is A by A plus C and 1 minus specificity is 1 minus D by B plus D. That is the B by B plus D. That is the number of people who are positive for the test among the healthy group, do not have the disease. In our question, sensitivity is 90 by 100 and specificity is 80 by 100. So 1 minus specificity is 20 by 100. Hence, positive likelihood ratio is equal to 90 by 100 by 20 by 100 is equal to 90 by 20. That is 9 by 2, which is 4.5. That is the probability or the positive likelihood ratio is the probability of a person with disease testing positive divided by probability of a person without disease testing positive. So there is a likelihood of a patient to test positive of 4.5 times in people with the disease compared to people without the disease. That is asked as an MCQ. Is a positive likelihood ratio of higher number good? The positive likelihood ratio of 200 would mean that the probability of the test to be positive in a group having the disease is 200 times that of a group which is healthy or do not have the disease. That test is really good. A positive likelihood ratio of 1 would mean that it is actually same in both the groups. So that test is not at all good. Okay. So students should not confuse positive predictive value with positive likelihood ratio. Positive likelihood ratio is this thing. The probability of a test to be positive in a group with the disease, that is your sick group or A plus C, divided by probability to be positive in a group that is healthy, that is B plus D. That is B by B plus D. That is positive predictive value, that is the total number of positives, that is A plus B. What number is truly positive? That is A. That is A by A plus B. All the positive results you get as a doctor in your OP, what proportion could you trust as positive? As we discussed in the last class, the probability of that actually determines is determined based on the prevalence of the disease. So the sensitivity and specificity are actually the nature or say the characteristics of your test, but positive predictive value depends on prevalence of the disease. If disease is very rare, all the positives you get would be false positives. So PPV would be low. The disease is very common. The probability for all the diseases positives you get to be truly positive is high. The PPV would be high. So prevalence will determine your PPV. Okay. Study was conducted in a hospital to estimate the prevalence of hand washing among healthcare personnel. All the study participants were informed that the study duration is 1 month and the method employed would be a passive observation of the daily routine at the hospital. Out of 127 healthcare personnel in the hospital, only 89 gave consent for the study, and so they were followed up for 1 month. This study could mostly suffer from dash. This was a favorite question for AIMS when there was AIMS exams. But now, would you get this question? I don't know. But there is a possibility for this to come. You just have an idea about what this is. Any of you know the answer for this? Okay, I'll explain. Hawthorne effect, also called observer effect, will affect this study. The individual, when he knows that he is being observed, he will improve his practices. So that we actually observe, what we actually observe will not be the true picture, which would have been in the absence of being observed. This was first documented in a Hawthorne manufacturing plant. That's why it's called the Hawthorne effect. That is the answer. A Herkisonian bias is selection bias, which occurs due to the different probabilities of admission of cases and controls to a hospital. So this word will be there in the question. There will be cases and controls, and there will be different rates of admissions for both in the hospital. This becomes a problem when hospital-based controls are taken. Those spurious associations can be obtained as a result. Attrition bias occurs in a prospective follow-up study when some subjects no longer report back, and so we miss their data in the final analysis. This can potentially change our results in attrition rate is high. Rosenthal effect is whereby expectation of an experimenter knowingly or unknowingly influences the study participant and ultimately affects the outcome of the study. That is, if you keep on telling a child that the child is good, the child will become good. Because experimenter wants the result to be positive. This is also called a Pygmalion effect. There's a story with Pygmalion and all. It's not time to say that. The same thing. So it could be also called Pygmalion effect, Rosenthal effect. That is, you think something is good, and then you actually, when you read it, when you tell an employee that he is very good, his performance will actually become better. The negative of Rosenthal effect is called Golem effect, Golem effect. It is when you tell someone is bad, continuously he will become bad. So the experimenter or say the investigator is actually there, say, tampering with his study itself. And the result he is getting is actually true, but it is actually being like that because of the way he is treating the subjects or treating his observations. Unfounding, in a third variable associated with exposure and outcome and can produce independent, and through independent pathway can produce the outcome. It is basically your unfound. So move on to the next one. In a study assessing the relationship between dietary oil intake and serum VLDL, 100 middle-aged women belonging to a particular community, it was found that mean oil intake was 25 ml per day, the standard deviation of 4.3, and median was 18 ml per day. Data was explored in a statistical software, and the p-values of normality tests were significant. So if the p-values of normality tests are significant, that means that the quantitative variable is not normal. Okay. The tests we use for normality are Kolmogorov-Smirnov test and Shapiro-Wilk test. So if you get a significant p-value on that, it actually means the quantitative variable under question is not normal. So serum VLDL levels were found to be normally distributed. The researcher was planning to look for a correlation between these two variables. In this case, what advice would you give to him? These are the choices given in different ways. I will go to the answer. We approach this question in this way. The statistical correlation is done to find any association between two quantitative variables. That is, whether one variable change with respect to a change in the other variable. Positive correlation means when the value of one variable increases, value of other variable also increases. In negative correlation, increase in the value of one variable results in decrease in value of the other variable. When two variables are normally distributed, we can find a Karl-Pearson correlation coefficient. Value of correlation coefficient ranges from -1 to +1. Value of -1 stands for perfect negative correlation, and a value of +1 means perfect positive correlation. A value of 0 means there is no correlation. All these sentences are different MCQs. A value from 0 to 0.3 means no or very low correlation. 0.3 to 0.5 means high correlation. 0.5 to 0.7 means moderate correlation, and above 0.7 means high correlation. This is not a standard classification. You will have other classifications also. This is one of the classifications to give you an idea. If either of the quantitative variables is not normally distributed, then also we can do a correlation, but here we do a Spearman's correlation and find Spearman's correlation coefficient. That is the answer. For A, correlation can be done even though one variable is not normally distributed. That is the answer. B, C, D, and E, if you read that, are all wrong. We'll move on to the next question. I know I am a bit fast, but I have no other choice. Okay, I would actually like to spend half an hour on each of these questions, but time doesn't permit me to do that. I'm very sorry. Actually, I also don't like to explain things in a hurry, like I'm doing now, but I have no choice. I just need you to be familiarized with these questions and read of your own. And if you have any doubts, I will share my mobile number also with you. We can WhatsApp me with your doubts and I will get back to you. A clinical trial was done to test the efficacy of a new drug alpha to treat tinea versicolor. 500 subjects were recruited for this study, randomized to two groups in equal numbers. So it's a randomized controlled trial. Group 1 was given alpha and group 2 were given the conventional antifungal therapy. After the specific intervention, 210 from the study group and 220 from the control group reported back. 190 from the study group and 165 from the control group were cured. What is NNT for the new drug? NNT is the number needed to treat. It is also a favorite MCQ in the difficult section. The idea is actually very simple, but if you don't have the idea, it's an extremely difficult question to answer. Okay, so do you have the idea? I don't have time to ask you. I'm sorry. I'll go to the answer. NNT is the number needed to treat. It is the number of individuals who should be treated to get one more individual cured when compared to the control group. That is, treatment group, we cure extra. For that, we need to see how better is the treatment group from the control group. So it is a reciprocal. How it is calculated? It is a reciprocal of the absolute risk reduction due to the drug. So 500 subjects were randomized and divided equally to both arms. 250 in the study arm. Only 210 reported back, of which 190 were cured. So as per the intention to treat analysis, the cure rate is 190 by 250. Intention to treat, we take the actual number recruited. The other analysis is called per protocol analysis. The per protocol analysis is where you only take back those who reported back. So as per that, it would be 190 by 210, but we are taking intention to analysis here. Because to compare both we are taking in a similar way, it's fine. Of the control arm, with the conventional antifungal therapy, the cure rate is 165 by 250. Other is 190 by 250. So what is the risk reduction here? Absolute risk reduction is 190 by 250 minus 165 by 250, which is equal to 25 by 250. So NNT is the reciprocal of that. That is 1 by 25 by 250, which is 250 by 25, 10. So every 10 patients we treat with alpha, we get one more cure, additional cure compared with the conventional antifungal. So if we treat 100 patients using alpha, we get 10 additional cures compared to the conventional. That is NNT. Okay. This is one of your last questions. This question, I will just say what this question is about. This is about odds ratio. How do you interpret odds ratio? That is the question. You have got 2.7 as your odds ratio. How do you interpret this? So the answer is odds ratio is the ratio of odds of exposure among the cases and the controls. In this study, cases are those with bladder cancer and controls are those without bladder cancer. Exposure is smoking. Odds ratio is 2.7. The actual question was asking you, how do you interpret this? So, odds ratio of 2.7 means that ratio of odds of smoking in the bladder cancer group to that of odds of smoking in the group without bladder cancer is equal to 2.7. Okay, in case control studies, we cannot calculate relative risk. So we opt for the next best measure, which is odds ratio. In 2/2 table, odds ratio is calculated as the cross product AD by BC. Only relative risk of 2.7 should be expressed as 2.7 times increased risk among those who were exposed and not odds ratio. That is the point of this question. We can only say 2.7 times risk if it is relative risk. Odds ratio, you cannot say that this 2.7 times risk, but you can only say that the odds ratio is the 2.7 is the increased odds, or the ratio of odds is 2.7 times. Or you can also say something like 2.7 times more likely. But don't use the word risk or increased risk as per se, because that is reserved for the time relative risk. Because we cannot calculate relative risk from a case control study, we go for the next best measure, is odds ratio. That can also be asked as an MCQ. Question 17 is another question which is actually asking you about the confidence intervals and how to interpret the confidence interval and all, the odds ratio and all. So the thing I want to tell you is, for low education, that is a variable here. Odds ratio was 2.1. Confidence interval given was 0.9 to 9.7. So odds ratio 2.1 tells us it is a risk factor, but we should comment on it only after looking at the confidence interval or the p-value. If confidence interval is not given. Like we take a p-value less than 0.05 to be significant, we can take a confidence interval as significant if it does not contain the null value. So for a ratio, the null value is 1. That is, numerator will be similar to denominator. It is 1. So the odds ratio confidence interval should not contain 1. If it contains 1, it is not significant. That factor is not significant. That is thing you have to keep in mind. When you're asked about confidence interval, just look at the interval and see whether it contains the null value. If it is a ratio, it should not contain 1. If it is an absolute risk reduction or say difference, something like that, a difference null value is 0. When both values are same, difference would be 0. So a difference, if it is a difference, then it should not contain 0. If it is a ratio, it should not contain 1. For odds ratio, null value is 1. That is when both odds of exposure would be the same. For all ratios, null value is 1. For all differences, null value is 0. As we know, confidence interval holds equal significance for the values within the given limits. A confidence interval of 0.9 to 9.7 means there has to be equal significance for odds ratio values of 0.9, 1, and say 2.9. That is how the confidence interval works. The sample value was say something like 1.4. But what is the confidence limit? According to confidence limit, what would be the actual value in the population? That is what we find out by mean plus or minus 2 SC. If that contains the null value, then it is not significant. Fine. Hence we conclude that association is not statistically significant and low education is not a risk factor for young age myocardial infarction from the given study, because confidence interval was 0.9 to 9.7. It has to be significant. If it was 1.1 to 9.7, it would have been significant. Or say if it was 0.2 to 0.9, then also it would have been significant because it did not contain 1 in those two cases. So if it is 0.2 to 0.9, odds ratio is less than 1, then that means it is a protective fact. If it is above 1, that means it is a risk fact. But it should not have 1 or contain 1 in that, because 1 would say that the odds ratio is equal to 1 means odds of exposure of cases and controls both are equal. Okay, so we come to an end. You know, the last few things I was really quick and fast to tell you the kind of questions basically and the general of how they would be asking you for the answers. Okay, I'm closing my share. I think it would be very difficult for you to understand the things, and I am sharing my mobile number. It is 98954 26008. You can take it down, 98954 26008. If you ring me, I will not be available most of the times, because only free day I am getting is Sunday. That also maybe the evenings. All other time, like I'm having the administrative charge of one of the health centers, I'll be in a meeting or I'll be in some discussions and all. So what I am asking you to do is send me a message in WhatsApp. Just type your question, or maybe if you have some screenshots of your doubt and all, just type those questions in your WhatsApp and put those images, and you can also send me audio messages in WhatsApp with your doubts. Whenever I get some free time, I might see the messages also, but I might not reply because I will be somewhere busy. So don't think that there is a blue tick and there is no answer. I will not ignore it. I will answer when I am free. If you don't get an answer, just remind me later, saying, sir, this question has not been answered. Just put an up in that same window, then that message will come to the top. I will see the message, I will reply. Okay, whenever I'm having some free time, I will reply. You can ask me anything related to community medicine, whatever I'm taught or I have taught now, or anything. Even if other subjects you have some question with research and statistics and designs coming into that and all, you can ask me, no problem. Okay.